Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is reaction mechanism basics, electrophiles, nucleophiles and reaction intermediates. Chemical reactions are all around us, shaping the world in ways both visible and invisible. Understanding the mechanisms behind these reactions is fundamental for mastering organic chemistry, especially for students preparing for competitive exams like NEET and JEE. One of the most crucial aspects of organic chemistry is the concept of reaction mechanisms, where we analyze how molecules interact at the atomic level. At the heart of these mechanisms lie electrophiles, nucleophiles, and reaction intermediates. Electrophiles are species that seek out electrons. The term comes from electron-loving entities that have a deficiency of electrons. This makes them highly reactive toward negatively charged or electron-rich species. Electrophiles are often positively charged or neutral species with a partial positive charge. Common examples include carbocations, positively charged metal ions, and molecules like sulfur trioxide or acyl chlorides. Their reactivity plays a crucial role in several organic reactions, such as electrophilic addition and electrophilic substitution reactions. On the other hand, nucleophiles are electron-rich species that donate electrons to electrophiles. The term nucleophile means nucleus-loving, indicating their affinity for positively charged centers. Nucleophiles can be negatively charged ions, such as hydroxide, cyanide, or alkoxide ions, or they can be neutral molecules with lone pairs, like ammonia or water. Nucleophilic behavior is observed in substitution and addition reactions, where these species actively seek positively charged or electron-deficient centers to form new bonds. Reaction intermediates are short-lived, highly reactive species that form during the transition from reactants to products. These intermediates dictate the pathway and speed of the reaction. The most common types of reaction intermediates include carbocations, carbanions, free radicals, and carbene. A carbocation is a species with a positively charged carbon atom, making it a highly unstable and reactive entity. Carbanions, in contrast, have a negatively charged carbon atom and react readily with electrophiles. Free radicals are neutral species with an unpaired electron, often leading to chain reactions in organic synthesis. Carbenes are another fascinating class, featuring a divalent carbon atom with two non-bonded electrons, making them highly reactive. Now, let's discuss reaction intermediates, which are highly reactive short-lived species that form during the course of a reaction. These intermediates play a crucial role in determining the pathway and outcome of a chemical reaction. There are several types of reaction intermediates, including carbocations, carbanions, free radicals, and carbenes. To understand the interplay between electrophiles and nucleophiles, let's consider a fundamental reaction, the nucleophilic substitution reaction. In this reaction, a nucleophile replaces a leaving group in an organic molecule. A classic example is the reaction between hydroxide ion and an alkyl halide. The nucleophile, hydroxide, donates a pair of electrons to the carbon bearing the halogen, displacing the halogen as a leaving group and forming a new bond with the carbon. This forms an alcohol, completing the reaction. A different but equally significant reaction type is the electrophilic addition reaction, commonly observed in alkenes and alkynes. Here, an electrophile interacts with a double or triple bond, leading to the formation of a new product. For example, when hydrogen bromide reacts with ethene, the pi bond breaks, allowing the hydrogen to attach to one carbon and the bromine to the other, forming bromoethane. This process showcases the reactivity of electrophiles and the importance of understanding how reaction mechanisms operate. The stability of reaction intermediates determines the feasibility and rate of a reaction. Carbocations, for instance, follow a specific order of stability. Tertiary carbocations are more stable than secondary, which are more stable than primary. This stability arises due to the inductive and hyperconjugative effects of alkyl groups attached to the positively charged carbon. Similarly, free radicals exhibit stability trends based on the availability of electron donation from surrounding atoms. One of the essential applications of nucleophiles and electrophiles is in the formation of complex organic molecules. Many pharmaceutical drugs and synthetic materials are designed using these principles. Understanding reaction mechanisms allows chemists to predict the behavior of molecules and design efficient pathways for synthesizing desired compounds. This knowledge extends to fields like biochemistry, where enzyme-catalyzed reactions rely on nucleophilic and electrophilic interactions to facilitate metabolic processes. Another crucial aspect of reaction mechanisms is the energy profile of reactions. Every reaction involves an activation energy barrier, which must be overcome for the reaction to proceed. Reaction intermediates often appear at peaks of energy diagrams, illustrating their transient nature. The lower the energy barrier, the faster the reaction occurs. Catalysts play a vital role in lowering these barriers, allowing reactions to proceed under milder conditions. Enzymes in biological systems function as highly specialized catalysts that facilitate biochemical transformations essential for life. For competitive exams like NEET and JEE, a solid grasp of reaction mechanisms is indispensable. Many questions test the ability to identify reaction types, predict products, and determine reaction conditions based on the behavior of electrophiles, nucleophiles, and intermediates. Developing this understanding requires consistent practice, analyzing reaction patterns, and recognizing trends in reactivity. By focusing on these core principles, students can build a strong foundation in organic chemistry, paving the way for success in exams and beyond. Thank you. We hope this video has helped you gain a clearer understanding of hydrogen and its compounds, especially the fascinating role of heavy water and isotopes. If you found this video helpful, make sure to like, share, and subscribe to AskPrep for more in-depth chemistry lessons. Keep studying, stay curious, and good luck with your exams.